distance dependence of the magnetic dipole of a small bar magnet, as well as model the magnetic field of this bar magnet using the distance dependence. Finally, we will compare it to the magnetic field measured in the lab. In this lab, we will go over magnetic fields as well as the formula to represent them using the Biot-Savart law, as well as magnetic dipoles and distance dependence. In this lab, we will calculate the distance dependence of the magnetic field to be 9.39 times 10 to the negative 7th. Using this in the Biot-Savart formula for the magnetic field of a dipole, we will model the magnetic field at a distance d in glow strip to be around 3.9895 times 10 to the negative 3rd teslas. And we'll compare this to the measured magnetic field at this distance, about 3.317 times 10 to the negative 5th teslas. As particles move through the air, they create a magnetic field whose direction follows the right-hand rule. This is modeled by the Biot-Savart equation for a moving point charge, in which the cross product means only the orthogonal components of the velocity and observation displacement vector contribute to the magnitude of the magnetic field. Likewise, we can also model the magnetic field for a magnetic dipole, both on-axis and perpendicular. The concept of the magnetic dipoles closely mirrors that of electric dipoles in the sense that the resulting fields on axis are in the same direction as the dipole moments, but in the opposite direction when perpendicular. This case describes how the magnitude of the magnetic field due to a bar magnet falls off with distance. In the line of best fit for the graph below, the natural log of the x component of the magnetic field is n times the natural log of the observation distance r plus the natural log of the distance dependence k. In turn, we can calculate the magnitude of the magnetic field to be the distance dependence times the observation distance raised to the n. But the observation points are sufficiently far enough away such that the Biot-Savart formula holds, and we can use the included formula to model the magnetic field of the bar magnet at an arbitrary observation vector. We will create a system with just the bar magnet, then measure its on-axis magnetic field using the phone and meter stick in the surroundings. We will then use these measurements in order to determine the distance dependence and eventually the magnetic dipole moment. We will measure the magnitude of the magnetic field due to the bar magnet at a distance d away at a 45-degree angle. We will input this distance d into our Python model and compare the estimated magnitude of the magnetic field with the measured one. In the experiment, I observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. However, as the magnetometer moved closer to the magnet, the measured x component of the magnetic field did not decrease. Nor was it true that the position of the magnetometer had no effect on the measured x component of the magnetic field. However, I did notice that as the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased. The strength of the on-axis magnetic field and observation distance as we experimentally measured, we can use Excel to create a line of best fit such that the natural log of the x component of the magnetic field equals negative 3.1557 times the natural log of r minus 13.878. We also know that r is 1 meter. From there, we can determine the distance dependence since it is the y-intercept of the line of best fit, and we can also find that n equals negative 3.1557 since it is the slope of this line as well. Plug these values in to find the magnitude of the magnetic field and then substitute in the Biot-Savart formula for the strength of the magnetic field of the magnetic dipole. From there, we can do algebraic simplification and we find that the magnetic dipole is about 4.697 amps per meter squared. Substitute this magnitude into the Lab 3 starter code, as well as create a function to calculate the magnetic field of a dipole using the Biot-Savart formula for a magnetic field of a dipole at any observation vector r. We get the unit vector of r by dividing it by its magnitude, and then we can also compute the dot product of the magnetic dipole and r hat before plugging all these values into the formula I listed in the introduction. The scale applied to the magnetic field vector as well as the distance between the bar magnet and the observation vectors so that we can get a general sense of the magnetic field in the screen on the right. We want to observe the magnetic field at 4 positions perpendicular to the bar magnet and 2 locations on axis. We then find the observation vectors for the 2 on-axis locations and plug them into the function we made earlier. Then we follow suit for the rest of the perpendicular observation points. Finally, we input the measured perpendicular components of distance d and plug the new position vector into our magnetic dipole function to estimate the magnetic field due to the dipole at this location. We determined the distance dependence to be 9.394 times 10 to the negative 7th. We created a glow strip program that utilized the distance dependence and Biot-Savart formula for the magnetic field of a magnetic dipole to model the magnetic field of this bar magnet. We predicted the magnetic field at a distance d away at 45 degrees to be 3.89895 times 10 to the negative 3rd teslas. We also measured the actual magnetic field at the observation location to be 3.317 times 10 to the negative 5th teslas. Inaccurate due to difficulty locating the magnetic sensor in the phone, as well as inaccurately measuring the distance to the observation locations. There is also significant magnetic interference in the lab from miscellaneous electronics and metal. We also assume that the dipole approximation holds. Orientated the experiment to compensate for the magnetic north, then I would have assumed the magnitude of the magnetic field on the axis was equal to the x component, when in reality the magnetic field would have also had a y component. This error would have resulted in a much more inaccurate estimation for the distance dependence, and in turn would have resulted in a much more inaccurate estimation for the magnetic field at the 45-degree observation point. If I were to stick two identical magnets together such that they have the same magnetic dipole moment in the same direction, then the magnetic fields due to both would be additive. In turn, the measured dipole moment would be greater, and the final magnetic field would be greater as well.